Okay. Um, Good afternoon. After we finish the series of LR circuits, today I will explain you how if the capacitor is connected in series with the resistor. So the procedure is similar to the inductor. We have to find the voltage of resistor of VR is equal to Ri, and then the voltage of the capacitor, if you take you already know in physics, 1 per c integral of I dt. So this is the voltage of the capacitor. And then if do the similar thing to the inductor and resistor in series, we see that the V is VR plus VC here. So we have that V is equal to Ri plus 1 per C integral of I dt. Okay, and then if we make we differentiate this equation, because this is the integral, so it's easy for us to make a differentiate these equations. So we get that if we differentiate this equation with respect to t, we can see that this equation must be, this is the 0, so we do differentiate the constant, so this must be the 0, and this is what must be r di per dt plus I per c. So this is if we make a differential respect to t here, to the time. And then after we got this differential equation, we can solve this differential equation to get the solution. Solution is mean that I is equal to blah blah blah. Okay, we start with this equation, r di per dt plus I per c is equal to 0. And then we divide both of side by using the r. So we got that di per dt plus 1 per rc is equal to 0. This is I, okay. 1 per rci is equal to 0. So this is the first order linear differential equations. So we can solve it by using the integrating factor. So this is the p, right? Integrating factor. So this is the p. P is 1 per RC. And then this is the key. Okay, please remember the integrating factor method. So the key is equal to 0. So we have to find the integrating factor. Integrating factor is IF is E integral of p dt, right? So E integral of 1 per RC dt, like this one. So we got that E is 1 per RC t, or E is equal to t per RC, like this one. This is the integrating factor. So actually we have to, in the integrating factor method, we have to multiply this integrating factor to the equation. It means that the IF dot di per dt plus IF dot 1 per RCI equal to 0 dot IF, like this one, right? When I explain about the integrating factor method. And okay, we got that for this point, this is the key. So we got that this is the 0. So if we make the integral of k dot integrating factor, so we can get that the integral of k e integral of p dt like this one. So it must be integral of 0 dt. So it's k. This is the constant. So by applying the linear first order equations, we got that this one, okay, this one will be I dot e t per rc. So this is equal to k. Okay, since that I is equal to Vr when the t is equal to 0, so we got that k is must be V per r. So this is the 0, and then I is V per r, see this one, and then we got that k is must be V per r. And then if we substitute back, we notice that I dot trc is equal to V per r. And then solving this equation, we got that I is equal to V per r e minus t per rc here. So this is the solution of our differential equation. Okay. So this is the tau. So this is the tau. The tau is rc for the series capacitor and resistor, and for the inductor is L per R. So we got this one. So this is the solution of the capacitor. Okay, if we apply back to this equation in this first time here, so we can see that what is the VR and VC. VR is IR, so we got that V per R E minus T per RC dot R. So this one, so we can get that the voltage of resistor is V E minus T per RC. And then how about the VC? VC is 1 per C integral of I dt. So we can get that we make integration of this one. Yeah, integration of this one. We got that V is 1 minus E minus T per RC. Okay, so this is the voltage of the capacitor. Okay, so this is the solution of the final how to explain the first order equation in the series of inductor and the capacitor and resistor. Okay, uh, I think this is enough for the explanation of the applications. Thank you. See you next time. Good afternoon. Assalamualaikum warahmatullahi wabarakatuh.